Recording.
Good afternoon, YouTube. It's your boy Luke. Start leaving work. It is home time. Get out of here. It's the Carby guru himself, Donkey. Okay, Donkey Race Engines, aka Damien. Check out his YouTube channel. But anyway, home time. How's everybody doing? This is a beautiful February-ish day here in Adelaide. It's not particularly warm though, but it's not too bad. So I thought I would have a bit of a chat and probably hopefully answer some questions I'll be getting in the comments. Speaking of the comments, I see most of you watching my videos are not subscribed. Give me a like and a subscribe if you could. Helps me out, helps build the channel. Comments much appreciated. Let me know what you want to see more of. But yeah, majority of the comments, well, questions at least, not necessarily comments, but questions I'll be getting are, how is the 109 surviving with 240 odd horsepower? So it's been about a year now I've had it running with the two turbos. 200 horsepower for most of that, just recently up to 240, but it has been engine wise absolutely flawless, no issues whatsoever. External systems wise, had some teething issues with the oil control early on. That's simply because the turbos are mounted so low they won't gravity drain back to the sump. They have to be fed back with a scavenge pump. So that took a little bit of mucking around to get that how I wanted it, but it works really nicely now. Ended up using a marine diesel pump, transfer pump used for transferring fuel between tanks in boats, and that works really nicely. That worked better than the fuel pump I had in originally. Obviously a fuel pump's not designed to pump hot oil, so it's not the most friendly operating conditions for a fuel pump, but yeah, the diesel transfer pump works really nicely. The other teething issue we've had is thermal issues, and it still does tend to run hot. I've tried to fix it as much as I can in terms of adding an external oil cooler and just sort of trying to optimize everything in terms of the cooling system, but the cooling system on these is very small capacity. It's only 2.7 litres or something, which is, it's going to struggle with the additional heat from two turbos, the manifolds, all the pipework, heating the oil, all that sort of stuff. But it's perfectly manageable. The only time you'll have an issue with it is on a really hot day, if you're sitting still in traffic. And even then, most of the time it's fine. It's just if you're beating on it and then sitting still in traffic, then you've got problems. But that is what it is. I couldn't really fix that if I wanted to, short of aftermarket radiator, I suppose, if such a thing existed, which it doesn't, but we could make such a thing. But anyway, it's fine. Gearbox, now that's a big one. The gearbox in this is not standard by any means, so anyone asking how second gear is coping, well, second gear didn't cope. It didn't cope with the motor before the turbos, and it absolutely would not cope now. So this gearbox is extensively modified. I have a lot of billet parts from RC Industries online or something in the States. Did all my billet gear set, billet forks, billet shift rods. The guys down at Race Bike Services in Lonsdale put it together for me. Did a superb job on it. It feels exactly like it did the day it left a year ago. Same deal with the clutch. The standard clutch would not cope. this has high grip frictions, some aftermarket springs, some spacers, same deal. The guys down at Race Bikes sorted that for me. I just said make it deal with 200 horsepower every day, and they really came to the party on that one. Other than that, the engine is standard. It still has the same spark plugs it had from the factory. They're new ones, obviously, but the same heat range, same type, all that sort of thing. And to explain how this works, I'll try and give you some background on the failures that I am aware of on 109 motors in the past, and sort of some of the factors that go into those failures, and some general tuning principles. So bear with me, I'll try and not waffle too much. Hopefully my voice doesn't annoy you like it annoys me, but I guess that's just a vlogging thing. So the crankshaft failures that happened years ago, I haven't seen any evidence of any recently, but they were with supercharged motors. There was a company in the UK that made supercharger kits for these back probably 10 years ago, and I contacted them when I was first thinking about putting turbos on it and had a chat with them, and basically they said they stopped making the turbocharger kits, the supercharger kits, because they were seeing crankshaft failures. Now, the failures tended to happen on the far side bearing area from the clutch, so the generator, magneto, whatever you want to call it, side. And I would suggest that was because of the additional leverage placed on the crank by driving the supercharger. The supercharger has to be driven by a belt from one end of the crank, and in the case of a 109, it has to come out a fair way from the bearing. So you're basically putting a bunch of leverage on one side of the crank. In addition to that, a supercharged motor is always going to be under more stress than a turbocharged motor, simply because it takes power to drive the supercharger. So if a supercharged motor is making 200 horsepower, it might be wasting 50 to 100, generally not 100, but that was sort of back in the old days of superchargers, but on a modern supercharger, potentially you can be wasting 20-25% of the power you're seeing driving the supercharger. So yeah, failures on a supercharged motor will generally occur at a lower power level than they would on a turbocharged motor for that reason. But in the case of the 109, I think it's almost certainly the leverage on the crank that's causing it, rather than outright power induced failure just based on the type of failures that I've seen. Anyway, that's my take on that. I've had a few comments saying I thought motors snap cranks at 160 horsepower or wherever it was. I would suggest that's probably where that came from. And in saying all this, hopefully I don't end up with egg on my face and a broken crank or a broken anything else, but I'm fairly confident, given we're a year in and it's had a lot of use, a lot of abuse. It's got plenty hot, plenty of times. It's had some questionable fuel quality, especially before the before the intercoolers. So it has seen some detonation, and I'll get into that next. But right now I have to put some fuel in it. Where are we? 98. Come around this side. Here we go.
Recording.
Okay. Fuel in. Thank you, buddy. Alright, so, just talking about ways to keep a motor alive. So yeah, apart from the obvious making stuff, you know, as strong as you can in terms of the gearbox and stuff like that, the actual design of the motor is pretty good for boost, believe it or not. You have forged pistons, which is probably the biggest factor. Water stroke ratio is pretty good. You don't have a ridiculously long stroke, so you don't have, you know, stupid leverage on the crank. Conrod angle's fairly decent. Obviously the cylinder head's really good. Cam profile's really good. All that stuff sort of lends itself to boost fairly well. Even the compression ratio at 10.5 is not ridiculous. It just comes down to some tuning stuff to make that work. But the biggest killers of engines are generally not the power level itself. What generally hurts an engine is something going out of parameters. Geez, that was close. The biggest killer of motors is detonation, or pinging, or spark knock, or whatever you want to call it. So let's talk a bit about that. What detonation is, and this is not to be confused with pre-ignition. They're two very different things. Detonation. So what happens when spark plug fires in the engine and ignites the fuel air mixture, and it starts burning in a controlled way. The flame front spreads out from the point of the spark plug, from the ignition source, and the gases expand. The best way to sort of describe this is, imagine blowing up a balloon. The air going into the balloon is the expanding fuel air mixture. Sorry, the leftovers of the fuel air mixture. Once they're ignited and burnt, the energy, expanding gases, so to speak. And the skin of the balloon would be what's called the carbon skin or carbon bubble. Now, what that is if you've ever watched a flame coming off a candle or something, you know, you've got your teardrop flame. It's hottest in the middle at the source, and around the edges you have black sooty looking smoke coming off it. And what that is carbon, which is a byproduct of burning fuel, burning hydrocarbons. Yeah, the soot, coal, whatever you want to call it, smoke even, is carbons coming off the burning fuel air mixture. Now what happens is that carbon forms a layer between the hot burning expanding gases and the relatively cool gases inside the combustion chamber, which are close to the cylinder head, face of the cylinder head, the piston crown, the bore walls. They have this boundary layer of air that's not burning. Sandwiched between that and the burning expanding gases is this carbon skin or carbon bubble. Now, this is important because the temperatures of the burning fuel air mixture, the expanding gases, all that stuff dramatically exceed the melting point of aluminium. Aluminium melts at between 500 and 600 degrees Celsius, and you'll see exhaust gas temperatures, particularly with turbocharged engines, above 1,000 degrees in some cases. But even post turbo, 700-800 degrees, not uncommon at all. So obviously, if those temperatures were directly in contact with the piston crown or the cylinder head surface, you would have melted metal. And generally speaking, you don't have melted metal in an engine, or you certainly shouldn't. So that's the importance of the boundary layer and the carbon skin or carbon bubble that separates it from the burning gases. Now, this is important because what happens when an engine detonates it is an uncontrolled burning of the fuel-air mixture that occurs after the spark plug has ignited. So you have a relatively slow controlled burn from the gases that, the fuel-air mixture that has been ignited by the spark plug, and you have a rapid uncontrolled burn where those mixtures have spontaneously ignited due to excessive pressure, hot spot. There can be a lot of things can set it off, but the important thing is it creates a pressure spike in the cylinder, and there is some debate as to whether this pressure spike comes from the two flame fronts colliding or just the rate at which the uncontrolled mixtures are expanding. In any case, what happens is that pressure spike breaks down, ruptures, tears the carbon skin, which is the separating between the extremely hot layer of gases and the relatively cool layer of gases. And as a result, the metal surfaces can be exposed to the extremely high temperatures, and you can start to melt them. And this is what happens when you see a hole melted in a piston or a cylinder head or any of that. It is generally caused by a detonation event, pinging event, that has then exposed the metal to those extreme temperatures. So detonation is to be avoided at all costs in a performance application. Now, interestingly, Suzuki state that some pinging is normal in the 109 motors, and I've certainly observed it in completely standard 109s. You ride them on a hot day and you hear some pinging under high load at sort of medium RPMs. It's not uncommon, and it's not extremely damaging under those circumstances when it's making, you know, sub 100 horsepower under those conditions. But when you're making 2.5 times that, it is obviously much more damaging. So detonation is to be avoided at all means. Now, how, at all costs, how do we do that? Well, number one is by ensuring we don't have excessive cylinder pressure caused by too much ignition timing advance. So, and this is a big thing with boosted engines, supercharged or turbocharged. They will want less ignition timing at full load, less ignition timing advance, which is when the spark plug fires relative to the position of the piston in the cylinder, than a naturally aspirated motor. Now, in naturally aspirated form, these motors want about 30 degrees timing advance, which is pretty typical for most motors. They're usually between 20 and 36 degrees. And yeah, 109s want right around 30 degrees. But with 10 psi boost or so, or 12 psi in this bike's case, we want around the 20 to 22 degree mark. So we're looking at reducing the total ignition timing at full load by 8 to 10 degrees. So you can probably imagine what would happen if you ran one of these bikes with turbos on the factory ECU program without retarding the ignition timing. You're going to have some detonation present, and I would suggest pretty significant detonation present. Now, people think that detonation or pinging, you can always hear it, and that's absolutely not the case. This little light here that just flashed red, as if to illustrate my point, is hooked up to a knock sensor on the rear cylinder, and it flashes anytime it detects what could be detonation. When you're on the throttle and everything's stable and accelerating, then if that flashes, it is detonation almost certainly, or it's the rev limiter or a gear change. But when you're idling around, it tends to pick up a little bit of piston noise and gearbox noise and that, and that's fine. But for the most part, if that light flashes, you've got some detonation present, and that picks up detonation when I'm tuning it on the dyno or riding it on the road long before I can hear it. I mean, I can't hear a thing, and these exhausts are very quiet, and yeah, no chance of hearing it. It's flashing away now, but that's piston noise or whatever at idle. So, and this applies to most motors. You generally will not hear detonation until it is very severe. So just because you didn't hear it didn't mean it didn't knock. And we see this in engine failures all the time. You'll have all the symptoms of detonation and the builder or the owner or the tuner will say, well, it never knocked. And it's like, well, yes it did, you just didn't hear it. So this is a big factor in keeping highly stressed engines together, is not being greedy with the timing and managing it properly and bringing it back to the point where it wants to be. So on this bike, it's retarded a few degrees from where detonation would start to occur, and that's pretty much what you want in terms of a safety margin. So that's the first step in ensuring an engine survives. Air-fuel ratio is a very important thing as well, and it's certainly a lot easier to understand. So the air-fuel ratio is the ratio of oxygen to fuel molecules in the motor. The theoretical ideal air-fuel ratio for 98 octane petrol, hey bud, how are you? Is 14.7 to 1, so 14.7 parts oxygen to 1 part hydrocarbon fuel is the theoretical best burning ratio. But all that means is that at that ratio it burns all of the available oxygen, or the most available oxygen that it can. There's not the ideal ratio for necessary. Cheers, bud. That happens a fair bit. What was I saying? Yeah, so that's just a theoretical optimum. You'll quite often get better economy running slightly leaner than that, or slightly richer. But that's generally where you have the best results in terms of emissions. So most vehicles tend to run around 14.7 to 1 cruise conditions to pass emissions tests. Not necessarily the best rideability, not necessarily the best economy, but that's a whole other story. But when it comes to boosted engines under load, you want to run them richer, and even naturally aspirated engines at full throttle, these like to run around 13 to 1, so a bit more fuel, a bit less oxygen. The reason for that is there's more turbulence in the combustion chamber, so you can burn more fuel, more to the point you would not burn all of the available oxygen with the theoretical optimal amount of fuel if you stuck to that theoretical optimum ratio, which is why it's theoretical. But aside from that, any unburnt fuel going out the exhaust takes heat with it. Heat in the combustion chamber is one of the factors that can lead to detonation. So, and it actually can create more power by running a little bit more fuel as well. For a number of reasons, it allows you to run more timing. No need to get too far into that. The point is, you need to tune it at a safe air-fuel ratio. That's easy enough. The problem with that is you have constantly changing conditions when you're out on the road that will affect your air-fuel ratio. So 10 pound of boost in first gear at 4,000 RPM is not necessarily equal to 10 pounds of boost at the same RPM in fourth gear. You will tend to see a leaner fuel mixture in a higher gear under those circumstances, and that can be because it occurs at a different throttle opening. You could be getting some ram air effect from the airspeed forcing air into the front of the turbos. You could be getting additional cooling into the intercoolers, which creates a denser mixture. All these sort of things. The bottom line is conditions change when you're on the road. So that's where this stuff comes into it. The auto-tune function, which I hate the term auto-tune because it gives people the impression that you don't have to tune the system. It doesn't work that way at all. It is the correct term for it is a wideband closed-loop system. So that means it has a wideband oxygen sensor, which is capable of measuring a wide range of air-fuel ratios, as opposed to the factory sensors, which are not. And it runs in a closed-loop condition, which means it adds or subtracts fuel to the tune based on what it sees on the oxygen sensor. So that is very handy because it controls, it trims the air-fuel ratio. It only works once the tune is really close, but once it is really close, it's very handy. The second part that is important in it is the fact that I can run an external manifold absolute pressure sensor or MAP sensor. Now, this is important because in the factory configuration with the factory manifold pressure sensors, or IAP, intake air pressure sensors as Suzuki calls them, they do not measure boost. The ECU stops relying on them at maybe 1 psi of boost, so a little bit. In any case, they're not there. So when you're mapping it by the factory ECU, we're just determining load by throttle opening, and that's not the best way of doing it with a turbocharger. It works okay with a supercharger because you generally have the same amount of boost at a given RPM and given throttle opening because you don't have a lag scenario, but you do with a turbo. So that's another factor in tuning it carefully. We're allowing for additional fueling adjustment based on a manifold pressure signal from an external sensor. I've used a Link 4-bar map sensor in this case, which is complete overkill, but it's what we happen to have at work. So that got wired in to the 0 to 5 volt input on the power commander, and away we go. It allows me to fine tune the fuel mixtures and keep everything where it should be within parameters under changing conditions. Now, in addition to that, what you need to keep an engine alive is things called fail safes. So, you need a boost controller, which is this thing here. Now, the reason I need a boost controller is to control the boost, believe it or not. But the common misconception about boost controllers is they cannot decrease boost pressure in the engine, they can only increase it. By that, I mean they cannot decrease it over the pressure that is dictated by the wastegate, which is that cylinder thing attached to the front of the turbo. That's the wastegate actuator. There's a spring in it and a diaphragm, and boost pressure, which is fed to it from the inlet manifold, opens the valve which diverts exhaust pressure around the turbo at a desired level. That level is referred to as spring pressure. And what the boost controller does, it bleeds off that pressure signal to that actuator and increases the boost pressure level. Now, this is important for a few reasons. It actually gives you control over the boost level, but in terms of keeping the engine alive, it allows you to introduce a fail-safe system. What that means is we tune the engine for 12 psi, but the spring pressure or gate pressure on these turbos is around 7 psi. What that means is without the boost controller doing anything, we'd have 7 pounds of boost. The boost controller targeting our 12 pounds of boost, we have 12 pounds of boost. Why does this keep the engine safe? Well, if something goes out of parameters, fuel air ratio for example, the boost controller can drop the boost pressure level back to our 7 psi base setting really quickly, much faster than I'm going to pick up on it and roll off the throttle. And it does that by having its own wideband air fuel ratio sensor and its own controller. So I'm running 2 separate wideband air fuel ratio systems on this bike. One for the boost controller and one for closed loop fueling. That's called redundancy. What it means is one of those systems can fail and I'm still going to have some protection built in, because if the boost controller sees air fuel ratios leaner than whatever I set it to, I generally set it to around 13:1 air fuel ratio at a preset percentage of its maximum boost, 80% set it to, so that works out to about 10.5 psi on a 12 psi tune. If it sees leaner than 13:1 air fuel ratio, it drops the boost pressure back, saves the engine. That, in conjunction with my knock sensor light, which gives me a visual warning if something goes out of parameters and causes the engine to detonate. The boost controller also flashes, gives me a visual warning if it goes lean, at the same time it drops the boost pressure back. Those sort of systems are what tends to keep the motor alive in a high stress environment. Additionally to that, I have these visual cue lights set up on the digital dash here, which reflects my air fuel ratio. This amber light corresponds to the correct fuel air ratios for cruising conditions. This light here, which is green, should come on when I accelerate. And that tells me that the ECU is setting appropriate air fuel conditions for acceleration. If this light here comes on, which is a red light, which doesn't come on fortunately, but if something goes wrong and that comes on, I know the air fuel ratio is too lean for the operating conditions I'm in. So that's the third fail-safe of sorts. These are the sort of things that you can engineer into a bike or a car or whatever you're tuning that are going to lead to the engine hopefully surviving long term. And again, I hope I don't get egg on my face saying all this, but I'd rather try and answer some questions and hopefully clear some things up for you guys. So it's this sort of stuff that quite often gets overlooked in these projects. People will sort of just do the bare minimum. Fuel system is another element we probably should discuss. So most turbo 109s that I have read about, seen, spoken to the owners, have the factory injectors in them, and the owners either increased the fuel pressure to get some additional fueling, or they've lengthened the pulse width with a power commander, or they flash the ECU to increase the pulse width, or whatever they've done. They've added some extra fuel when the motor's on boost via the factory injectors. Now, the problem with this is the factory injectors are not big enough for a boosted motor. The injectors that are in this are 1150cc capacity, and at 240 horsepower they are running at 80% duty cycle, which is about as much as you want to run a set of injectors to. Now, the standard injectors are 400cc, so they're just a little bit bigger than 1/3 the capacity of the right size injectors for this bike. So that should be able to, you should be able to deduce from that how bad the fuel situation is going to be if you try and run factory injectors on a turbocharged M109. It will not end well. So while you could have enough fuel for a low boost application, sort of 4 or 5 psi, I doubt you could do it, but it's possible if you run massive fuel pressure to them. You're not going to have any headway. So those injectors are going to be at 100% capacity to supply just enough fuel for the boost level you're running. Now what happens if the boost level increases for some reason by 1 or 2 psi? A leak in one of the hoses that goes to the wastegate or something like that. You experience a slight overboost situation, your engine is going to go lean. When an engine runs lean, sorry, I should clarify this. The difference between running lean and running not rich enough. People think, and I'm guilty of saying things like I just said about engine running lean doing damage. People say this, itchy nose against the wind noise. People say running lean makes an engine run hot. Running lean does not make an engine run hot. Lean air fuel ratio, hey buddy, would be considered any air fuel ratio leaner than non-air octane fuel 14.7 to 1, because that is the stoichiometric air fuel ratio. Lambda 1, the ideal theoretical air fuel ratio. So a fuel mixture of 14.8 to 1 will be considered lean. A fuel air mixture of 14.6 to 1 will be considered rich. Now, the air fuel ratio that creates the most heat in the combustion chamber is the theoretical optimum air-fuel ratio, which makes sense because you are extracting the maximum amount of energy from it under those conditions. When you lean off the air-fuel ratio, when you reduce the amount of fuel molecules in that combustion chamber beyond the theoretical ideal, 14.7 to 1 in this case, it changes with fuel, with different types of fuel, but we'll use it for this example, the temperature drops. When you increase fuel content in the equation richer than 14.7 to 1, the temperature drops. Now, why do we run an engine richer for safety and not leaner? Diesel, if we run them leaner, because it works, but the petrol engine, you get unstable combustion with leaner conditions, so we have to run an engine. The problem with that is when I say something like I said before, if it goes lean, you hurt the engine. No, if it goes not rich enough, you will hurt the engine. So if your air-fuel ratio goes from an optimal 12 to 1 at full throttle, under boost, to 13.5 to 1, temperatures will increase, you will potentially experience detonation, and you will potentially melt an engine component. So this is why we want injectors big enough for application, with a bit of headroom to spare. So if it goes, for some reason we get an overboost situation, which my boost controller will shut it down. If it sees an overboost, it will shut it back to 7 psi, but let's assume for some reason that doesn't work. An overboost situation, we've got some fuel injector capacity here to add the additional fuel to avoid a, air quotes, lean out. We'll call it a lean out, but everybody calls it. It's easier to say than a not rich enough out. But yeah, that's how you can hurt a motor, by having injectors that are not big enough, or that are just barely big enough. So bottom line, you need a lot bigger injectors if you're going to turbocharge one of these bikes. What else? That's probably about it. Apart from some mechanical sympathy, i.e. don't do 500 meter burnouts with it. You can do a burnout occasionally, especially unintentional burnouts, those are always good. But yeah, mechanical sympathy goes a long way to keeping the engine alive. Apart from that, I've just changed the oil frequently, every 3,000 k's give or take, 3 to 4,000. Always run Penrite, full synthetic oil. It's not to say you have to run Penrite oil, but I've had great success with it. Good quality fuel, always run BP 98 if you're in Australia. The octane rating is a little different in America. I think our 98 is equal to your 93 maybe. Yeah, always running good quality fuel. I guess that's about it really. That's how you keep the engine together. Anyway, let me know what you think in the comments. Hopefully this answers some of your questions. If you have any more, hit me up. Like and subscribe please. It's going to make it a lot easier for me to make more YouTube content in the future. Some big things coming this year. Making some changes. Going to be building a lot more bikes. Building and tuning. And hopefully making a lot better content for you guys as well. Please give me feedback. I am new at all this. I need to learn. I want to know what you people want to hear about. What annoys you, what I should do, what I shouldn't do. All those sort of things. Anyway, I'll give you some Turbo 109 soundtrack without my annoying voice, and we'll see you next time.